Let's say we have a solution of acetic acid, and we know what's going to happen in solution. Acetic acid is going to donate a proton to H2O to form H3O plus or hydronium, and the conjugate base to acetic acid, which is acetate, CH3COO minus. And so there's a concentration of acetate anions in solution. What would happen now if you added some sodium acetate, right? So if you added some sodium acetate, let me go ahead and write this out here. So CH3COO minus and Na plus. So if you add some sodium acetate to your solution, right, you now have some more acetate anions. So you're increasing the concentration of one of your products, right? You're increasing the concentration of your acetate anion. And according to Le Chatelier's principle, if you increase the concentration of one of the products, the equilibrium shifts to the left. So the equilibrium is going to shift to the left, and that means that some of this acetate anion is going to react with some of your hydronium ion, right, when your equilibrium shifts to the left. This decreases the concentration of hydronium ion, and if you decrease the concentration of hydronium ion, you're going to increase the pH of your resulting solution. So the acetate anion is the common ion, and this is the common ion effect. Right, so there are two sources for your acetate anion. So one is the ionization of acetic acid. That's one source for your acetate anion. And the other source is the sodium acetate that you added in. So we have two sources. And so we'd expect a pH that's higher than just a solution of acetic acid alone. And let's go ahead and do the calculation and see that that is true. So calculate the pH of a solution that is 1 molar in acetic acid, and there's the Ka for acetic acid, and 1 molar for sodium acetate. And so we're just gonna start by rewriting our acid-base reaction. So we have acetic acid plus water. So we're going to have everything at equilibrium with our products H3O plus and acetate CH3COO minus. And right now, let's just for a second pretend like we have only acetic acid. So these are the kinds of problems that we've been doing. We started with our initial concentration, and we put a 1.00 molar concentration of acetic acid. And then for our change, we said whatever concentration we lose for acetic acid, we would gain for the acetate anion, and therefore we would gain for the hydronium ion. So we're going to gain a concentration of the acetate anion here, but we have to add in something, right? Because we're also dealing with this 1 molar concentration of sodium acetate. So we have a source, another source for acetate anions, right? So really we have 1 molar. Let's go ahead and put in that concentration. So the acetate ions come from two sources. Once again, one is the ionization of acetic acid, and one is the sodium acetate that you add in to make your solution. That's how I like to think about it. So your initial concentrations would be 1 molar for acetic acid, 1 molar for the acetate anion, and then pretty close to 0 here for hydronium. So at equilibrium, let's go ahead and write what we would have. So at equilibrium, we would have 1 minus X for our concentration of acetic acid, X for our concentration of hydronium, and 1 plus X for the concentration of acetate. Once again, two sources for our concentration of acetate. We can write a Ka expression, so an equilibrium expression using Ka, because we're dealing with acetic acid donating a proton to water here. So Ka is equal to concentration of products over reactants, so H3O plus times concentration of acetate, so times concentration of acetate, right, all over the concentration of our reactants, leaving water out, so the concentration of CH3COOH. All right, so for hydronium at equilibrium, our concentration is X, so we put an X into here. For acetate, our concentration of acetate at equilibrium would be 1 plus X. So let's put that in. So we have 1.00 plus X. And then this would all be over the concentration of acetic acid, which would be 1 minus x. So over here we put 1 minus x. All right, let's get some more room down here, and so we can talk about this. We're going to make that same assumption that we've done before, that this concentration x is much, much smaller than 1. And if that's a really small number, 1 plus x is pretty much the same as 1. And 1 minus x is also pretty much the same as 1. So if this is a very small concentration, we don't have to worry about these. We can approximate them and say 1 plus x is equal to 1. Let me go ahead and rewrite this here. So this would be x times, over here 1 plus x is approximately equal to 1, so that's our approximation. And over here 1 minus x, if x is very small, is also approximately equal to 1. And this is all equal to the Ka value, which for acetic acid is 1.8 times 10 to the negative 5. And so the ones obviously would cancel each other out here, and so the concentration of hydronium, which is x, right? Remember, x represents the concentration of hydronium ions, is 1.8 times 10 to the negative 5. So to find the pH, all we have to do is take the negative log of that. So negative log of 1.8 times 10 to the negative 5. And so we can go ahead and get out the calculator and do that. Negative log of 1.8 times 10 to the negative 5 is equal to 4.74. So our pH is equal to 4.74. Now, if you go back to the video on weak acid equilibrium, we calculated the pH for a 1.00 molar solution of acetic acid only. And the pH for that came out to be 2.38. So this is because we didn't have any other acetate anions present here. So we have different pHs, right? The pH is higher. The pH is higher for this situation where we have acetic acid, where we have two sources again for the acetate ion, the ionization of acetic acid and also the addition of sodium acetate. Let's do another common ion problem here. So this time we need to calculate the pH of a solution that is 0.15 molar for ammonia and 0.35 molar for ammonium nitrate. So ammonium nitrate is NH4 plus and NO3 minus in solution. And so we start with ammonia. So let's go ahead and write what's going to happen when ammonia reacts with water. So ammonia is a weak base, and it's going to take a proton from water. So if NH3 picks up an H+, we form NH4+, or ammonium. And if we take a proton away from H2O, take an H+ away from H2O, we form OH-, or the hydroxide ion. So once again, we start with our initial concentration, and we're going to pretend like it's one of the problems that we've been doing in earlier videos. So if we have 0.15 molar concentration of ammonia, we go ahead and put 0.15 here. When we think about the change, whatever concentration we lose for ammonia is the same concentration that we gain for ammonium, since ammonia turns into ammonium. And then therefore that's also the same concentration we gain for hydroxide. So one source for the ammonium ion, it would be the protonation of ammonia, right? So that's one source. But we have an additional source because we also have 0.35 molar ammonium nitrate, right? So there's another source for ammonium ions. And so we have 0.35 molar, so we go ahead and put 0.35 molar in here for the initial concentration of ammonium. And we're saying that we have 0 for our initial concentration of hydroxide. So when the reaction comes to equilibrium here for ammonia, we would have 0.15 minus X. For ammonium, we have two sources, right? So this is a common ion here. So we have 0.35 plus X, and then for hydroxide, we would have just X. So since ammonia is acting as a weak base here, let's go ahead and write our equilibrium expression, and we would write Kb. Right? And Kb for ammonia is 1.8 times 10 to the negative 5. So this is equal to concentration of our products over reactants. So we have concentration of NH4 plus times the concentration of OH minus all over the concentration of our reactants, leaving out water, so we have just ammonia here, so concentration of NH3. So let's go ahead and plug in what we have. For the concentration of ammonium, we have 0.35 plus X. So we put 0.35 plus X. For the concentration of hydroxide, we have X. So we go ahead and put an X in here. And then that's all over the concentration of ammonia at equilibrium. And we go over here, and for ammonia at equilibrium, it's 0.15 minus X. So we write over here 0.15 minus X. And we can plug in the Kb value, 1.8 times 10 to the negative 5. So let's go ahead and plug in the Kb. So we have 1.8 times 10 to the negative 5 is equal to, once again, we're going to make the assumption. So if we say that X is an extremely small number, right, then we don't have to worry about it when we're adding it to 0.35. And so we just say this is equal to 0.35. So 0.35 plus X is pretty close to 0.35. So this is times X, and let me just make sure you understand this X is this X. And then once again, 0.15 minus X, if X is a very small number, that's approximately equal to 0.15. And so now we would have this, and we need to solve for X. So let's go ahead and do that. So let's get out the calculator here. We need to solve for X. So 1.8 times 10 to the negative 5 times 0.15. And then we need to divide that by 0.35. And that gives us what X is equal to. And so X is equal to 7.7 times 10 to the negative 6. So X is equal to 7.7 times 10 to the negative 6. X represents the concentration of hydroxide ions in solution. So this would be the concentration of hydroxide. So 7.7 times 10 to the negative 6 molar is our concentration of hydroxide. Our problem wanted us to calculate the pH. So if we know the concentration of hydroxide ions, we can find the pOH, right, by taking the negative log of the concentration of hydroxide. So negative log of the concentration of hydroxide ions will give us the pOH. So let's do that. So we have the negative log of 7.7 times 10 to the negative 6. And this gives us the pOH, where we round to 5.11. So the pOH is 5.11. Let's get a little bit more room here. So pOH is equal to 5.11. And then we're home free because pH plus pOH is equal to 14. So we just plug in our pOH, solve for the pH. pH is equal to 14 minus 5.11, which of course is equal to 8.89. And so we've calculated the final pH of our solution.